So some theorems that help us play with polynomials. So the first one is our remainder theorem. Because, let's be honest, the polynomial division process can be a pain in the neck sometimes, if all we're interested in is what's the remainder and things like that. So if we're dividing by a linear function, turns out all we have to do is substitute a into the polynomial and it will give us the remainder. So let's just prove that. So we know we can rewrite our polynomial as quotient times divisor plus the remainder. Now we're going to say the divisor is x minus a. So let's rewrite that. And let's see what polynomial a is. Well, if we substitute a in, the x minus a is going to become 0. And so I'm left with remainder a. But I also know the degree of the remainder is less than the degree of the divisor. And in our case, we're dividing by a linear function, which is degree 1. Therefore, the degree of the remainder must be 0. In other words, it's a constant. So what this means is it actually doesn't matter what number I substitute into remainder, it's always going to be the same value, and that value we know is polynomial a. And so there's our proof. We always get the remainder. So okay, now this is the same one we did yesterday, I think, if I remember correctly. But now we could find that remainder a lot quicker than doing the actual division. All I've got to do, substitute 2 in, and there's the remainder, negative 19. I don't have to go through all that hassle of the whole long division there. Now where it's really useful is this, the factor theorem. Because if it's a factor, we know the remainder is equal to 0. And so this allows us to find linear factors. If we can find when the polynomial's equal to 0. So we're going to show that x minus 2 is a factor of this particular polynomial, and then go and factorise the whole thing. So all I've got to do is substitute 2 in, and yes, it's equal to 0. So by the way, if you're doing this in a test, don't just go, polynomial 2 is equal to 0. I mean, of course it's going to equal 0. It's a factor. They want to at least see the substitution in, so you haven't sort of just gone, oh, well, I know it's going to be 0, I'll just write 0 down, Hence factorise. Well, I know x minus 2 is a factor, so now I can divide, and it seems a bit silly now because I'm still doing long division. X minus 2 and x cubed is x squared, and I thought the whole idea of this was to save on the long division, but here we go, 2x squared, so keep dividing. Oh look, remainder 0, what a surprise. We proved that earlier. So that seems a bit strange doing it that way. I found the other factor, x squared plus 2x minus 15, fantastic. So I can now factorise that, multiplies together to give negative 15, adds together to give 2, and we get our full factorisation. But as I say, we haven't really taken advantage of the factor theorem, because if you think about it, I didn't really need to do that factor theorem over here. I could have just done the polynomial division of x minus 2. They told me it was x minus 2 was the factor. When I did the polynomial division, I got a remainder of 0, so I can say, oh yeah, it is a factor. So what's a better way of doing it? A better way of doing it is, some people say, by inspection. So I say just by using a little bit of logic. Rather than doing the full polynomial division, I've just proven, remember, that x minus 2 is a factor. So I know that is a factor. But the other thing I know when I expand parentheses out, the leading terms times the leading term will give the leading term. And the constant times the constant will give the constant. So, well, let's look at the leading term first of all. I know x times whatever the leading term is in my other factor must give me x cubed. Ah, well, therefore that's got to be x squared. And I can do the same thing with a constant. So I know that negative 2 times whatever number is in that parentheses must give me 30. So I know that's negative 15. And now all I've got to do is work out the middle term, how many x. So I look at that and I say, well, geez, how many x have I got? If I was to expand that out, how many x would I get? Well, I'd get minus 15x. But I want minus 19x. So I need minus 19. Well, how many do I still need? I need another minus 4x. So therefore, that middle term times the negative 2 must give me minus 4x. The missing bit that I'm looking for. So minus 4x will be negative 2 times, what? 2x. Bingo, I've got the other factor. Without having to do the whole long division. So we can use this, as I say, a little bit of logic, I call it. Some people say, oh, by inspection. But personally, I think it's a lot quicker than setting up the whole long division. And so then we can complete it like we did the last one. Well, let's try another one. Now this one here, they haven't given us any hint. So we want to factorise 4x cubed minus 16x squared minus 9x plus 36. Well, the things I know that the constant factors must be a factor of the constant. Because eventually, when we expand out, we're going to go constant times constant times constant times constant, and we come up with a constant number. So I'm looking for numbers that go to 36. So I'm not just going to randomly pick numbers to substitute in and see if the factor theorem works. I mean, we want to be sensible about this. We know it has to be factors of 36. Now, I deliberately did this example because 36, of course, has lots of factors. So we've got 1, 2, 3, 4, 6, 9, 12, 18, and 36. So, but of course, when dealing with polynomials, there could be negative numbers as well. So let's double the possibilities then that we have to check. But it's not monic. So it's quite possible that the factor might not be a whole number. It might be a fraction. Because if you think about it, if I'm going to factorise this and I'm going to end up with 4x cubed, so inside one of the parentheses I must have had a 4x or a 2x in there to expand out and get 4x cubed. Now, let's say it's 2x. If 2x minus something is a factor, then it'll be x equals something on 2 would be the answer if we were to solve that. So it might be a fraction. So the other thing we have to check are factors of the constant divided by factors of the leading coefficient. So I could have 1 on 4, 2 on 4, 3 on 4, 4 on 4, 6 on 4, and so on. Mind you, some of those are already in our list because 4 on 4 is the same as 1, for instance. So I could cross that one out, and 12 on 4 is 3, and 36 on 4 is 9. So that gets rid of some of them. Oh, hang on. 2 is also a factor of 4. So I could have any of those over 2 as well. But again, some of those we've already got in our list, so I can cross out a few of those. Righto. Oh, that narrows it down a little bit. And they could be negative as well. So it narrows it down. There's a lot to choose from. Now, logically, what's the first one you're going to check? The number 1? No, number 4, come on. Much more logical. Let's just see what happens with 4. Let's sub it in. Oh, what do you know? It's 0. There you go, it works. No, I mean, of course you're right. Logically, I would have chosen 1 first, but 1 doesn't work. 4 ends up working, so I sort of save a bit of time there. Okay, I know x minus 4 is a factor. Let's work out the other factor. Okay, again, leading term times leading term must give me leading term. So x times something must give me 4x cubed. So 4x squared. Constant times constant must give me constant. So minus 4 times something must give me 36. Minus 9. All right. So let's just check now with how many x's I've got. Well, at this stage, I've got, if I was to expand out, minus 9x. And that's exactly what I want. So it looks like there is no middle term in this one. But you can always check another one. Let's check the x squareds. If I was to expand the whole thing out, yes, I'd get minus 16x squared, so that's fine. So in this one, there is no middle term there. But it will, of course, factorise to be 2x plus 3, 2x minus 3. And so there's the other two factors that we would have been looking for. They would have been fractions. One would have been 3 on 2. The other would have been minus 3 on 2 that we're looking for. Polynomial x is this lovely expression, x plus 1, x minus 3 times qx plus ax plus 1 plus b. When the polynomial is divided by x plus 1, the remainder is negative 11. And when it's x minus 3, the remainder is 1. So what is the value of b? Well, I can use my remainder theorem. I know that when I sub in negative 1, I'll get negative 11. And then I sub in negative 1, look at all the things that disappear. I'm actually only left with b. So I get b straight away. b is negative 11. Okay. Next part. What is the remainder when we divide by x plus 1, x minus 3? So say the remainder would be a x plus 1 plus b. We've worked out what b is. Now we have to work out what a is. So what other information have they told us? They've told us that when it's divided by x minus 3, the remainder is 1. So we know that polynomial 3 would equal 1. Let's substitute that in. And well, the first bit's going to disappear because of 3 minus 3. We'll get 4a plus b is 1. We worked out b was negative 11. So 4a is 12. A is 3. So our remainder must be 3x minus 8. So the ax plus 1 plus b. X cubed minus 2x squared plus a. Now, yes, I've got a congruent symbol there. All congruent means is exactly equal to. So it's not an equation to solve and find x. We're saying, hey, these are always the same, no matter what you substitute in. Find the value of a. It's divisor times quotient plus remainder. So by saying polynomial negative 2 is 3, I'm using the remainder theorem. Rearrange it. A is 19. 19. Ooh, this is the 1994. Polynomials divided by x plus 1, x minus 4. Quotients qx, remainders rx. Oh, you love these ones where you've got to explain yourself. Y is the most general form of rx given by ax plus b. So what they're looking for here is that you know that the degree of the remainder is always less than the degree of the divisor, because they've told us we're dividing by a quadratic. So they're looking for something like this. Well, if the degree of the divisor is 2, the degree of the remainder could be 1. I mean, it might not be, it might be 0 for all we know. But it could be a linear function, so the most general form would be ax plus b, a linear function. Okay. Given that polynomial 4 equals negative 5, show that remainder 4 will be negative 5. Okay, so there's our divisor times quotient plus remainder. So polynomial 4, sub that in, and x minus 4, that disappears. So remainder 4 will equal polynomial 4, which they've told us is negative 5. Now further, we've been told that when we divide by x plus 1, the remainder is 5. So now we have to find this linear function. Well, it might be a constant, but let's see what happens. So we now know remainder 4 is negative 5. Remember, we said the most general form of the remainder was ax plus b. So I know 4a plus b is negative 5. We just got to work out what a and b are. So the other bit of information they've just given me is that when we divide by x plus 1, the remainder is 5. So polynomial negative 1 must be 5. Sub that in, I get negative a plus b is 5. Simultaneous equations. Solve that, we get a is negative 2, tells me b is 3, so therefore my remainder is minus 2x plus 3, because we said it was going to be ax plus b. Okay, so 10d, And that's what I was talking about before with our factor theorem. I mean, our factor theorem said when you divide by x minus a. So if your factor is something like 2x minus 1, for the factor theorem, you'd sub in a half. Because basically you're subbing in whatever would make that factor equal to 0. So if the factor is 2x minus 1, well, a half would make that 0. So I'd sub in a half to find out what the remainder would be, or if it's 0, if it's a factor.